So, good evening, everyone. So, this is the second week of live session of many body method in the quantum chemistry. I am your course TA. My name is Sujan Mondal, and I'm a PMRF research scholar at IIT Bombay. So, in this week, whatever the summary was that I'll discuss in the later part of this um, session. So, in the first part, what I have planned is to introduce you um, the Pauli matrices. How do they come, and like in first place, why do you need it, right? So in the first week of your lecture, you have seen that a spin orbital is basically a product of your it to be very like to specifically to say that it's a tensor product. It's a product of your space part times the your spin part. And you have also learned that these spin orbital are crucial to get the Slater determinants and 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 to preserve the antisymmetry of the electronic wave functions. Now, how how do we get this spin part that I'll discuss in this session today. So you all know that the space part is basically a exactly solvable. So it's a linear combination of exactly solvable one electronic wave function. So for example, let's say you have a hydrogen atom, and you all know the exact solution of this hydrogen atom one electronic system is can be written as psi r theta phi, where r theta phi are basically the polar coordinates. So actually you transform these xyz coordinate to r theta phi coordinate to actually exactly solve the hydrogen atomic system. And I think you all know this quite well. So this gives us basically three quantum number that we denote as NL, NL and ML. So where N is your principal quantum number, L is the azimuthal quantum number, and ML is the magnetic quantum number. You all know, right? So this can be one of the space part that can be taken into. And so what is about the spin part, right? So you can write this space part in this Kate notation, or you can also write in r theta phi notation, right? Now the question is, how do you write the spin part? So actually spin, so let's go back in the history. So how does this spin actually came into the picture, right? Because in the non-relativistic Schrodinger equation, you have seen there is nothing related to spin. So in spin, actually in non-relativistic quantum chemistry, we impose this in a ad hoc manner. So um, in Stern-Gerlach experiment, so what is Stern-Gerlach experiment? So what was done is, you had a magnetic field here. So this is basically a magnet, and there was a detector which was placed, and a silver atom's beam was passed in between these two. So what people expected is that, because silver atom, you know that the state is, so the valence electronic configuration is 5s1. so which has a L value is equal to 0, so it shouldn't have splitted into two, or because in presence of the magnetic, if your L value is greater than 0, then only it should have splitted, right? But what people has observed is that they found two spots which was exactly in the same distance from the middle point. So this was the initial experiment that was being done, and then later people suggested that there is one intrinsic degree of freedom which they called as spin to any microscopic particle. So you should not be confused with that it's like the electron is spinning or something like that. It is actually a one extra degree of freedom than r theta phi or nl ml. So one extra quantum number was needed to define the electronic wave function, right? So but people realize is that it's one kind of a it's one kind of an angular momentum. However, it follows the same rule as the angular momentum. So we can generalize all the rules that is applied to the angular momentum, that is also can be applied to this spin quantum number or spin angular momentum. So just like the our spatial part L and ml, we can write the spin part as S and ms, where this S is your spin quantum number and this ms is basically ranges from -s to +s, just like your because this ml ranges from -l to +l, and this L is the your angular quantum number, right? Now you have seen for the spatial part there is a coordinates like r theta phi, but in spin there is no such coordinates that you can think of, that for example for the angular quantum number, so there is this Lz component where this is the actually the this is actually the projection of the L along the Lz. So there was defined that this is my z axis, but in spin there is nothing like a spin angular momentum or something like that. So you cannot define any relevant coordinates to this spin coordinate, right? So what else we can do is that, so let's say, so we can write the operator like s square operator in this basis, like s ms basis s square. So there is, let's say there is something called sz, but it is not actually defined. So but can we write this s square and sz operator in this eigen basis of s ms? So that is our goal actually, to find out that how can we write this s square, sz, sx and sy in this basis, right? Sorry. Now it was found out that the value of s for electron the value of s is half. So you have only two choice, minus half and plus half. So you have two state, half. So just like your SMS, you are writing these two state as plus half, plus half. There is no need to write this plus here. And another is half and minus half. Now this we call as up spin, or alpha omega. So here omega is actually a arbitrary coordinate that I have defined, and there is only two possibilities. So this is called alpha omega, and another is your downspin, which is beta omega. Now just like the azimuthal quantum number, the spin quantum number also follows the same rule. What do I mean by that? So when a square, so so basically a square and sz, they are operator, right? So but I am not writing the cap here, but you guys please make sure that they are operator. So a square when operates on s and ms, it gives you s times s plus 1 h cut square, and it gives you back the same wave function. So this is so SMS is basically the eigenfunction of a square operator. Similarly, the sz operator when operates on SMS, as you all know, it gives you ms h cross SMS. Now as this a square and sz are the this SMS is the eigenfunction of a square and sz, so it is very evident that this a square and sz in this SMS eigenbasis, they are they are diagonal. So let me show you. So let's say you have only two eigenbases, half plus half and half minus half, right? So for simplicity, I am writing this as half. I'm just writing this part because the this spin quantum number is same for both these state, so I'm writing it as minus half. So now let's write the a square operator in these bases. So how will you write it? A square, so you can write it as half a square half. You can also write half a square minus half a square half and minus half a square minus half. So this is a matrix. So when a square operates on half, what will be the value? So you put s is equal to half here. So when s is equal to half, you will get half plus 1 is called square. I'm just writing the eigenvalue. So this is 3 by 2 and half, which gives you 3 by 4 h cut square. So you can write a square as 3 by 4 h cut square. Now you have half half minus half minus half half and minus half minus half. So actually what's happening is that, so this a square operate on this half, it gives you this 3 by 4 h cut square as a eigenvalue, and then you are left with the inner product of half and half. So similarly this a square operates on this minus half. So this is your ms value, but s value is half, so that's why it gives you the same eigenvalue 3 by 4 h cut square, and then you are left with half and minus half. And you all know this, the eigenfunctions of any operator, so when they are non-degenerate, they are definitely orthonormal to each other, or even if they are not. So I have shown you in the previous class that you can make it orthonormal by a procedure called Gram-Schmidt orthonormalization that I've shown. And so very clearly you have this 1 0 0 1, right? So you can see that the operator is diagonal in this basis. So similarly, how the SZ operator will look like, let's write down half SZ half half SZ minus half, then you have half SZ half, so this is minus, then you have minus half SZ minus half. Okay, so you know this, when SZ operate on SMS, it gives you ms h square ms h cross s ms. Okay, so your matrix becomes, so this is half h cross, so you can take common h cross. So then here you will be so it will be left half and half, so they are normalized, so it will give you 1, and this is 0, and again this is minus half and half, it will be 0, and in this case this is minus 1. Why minus 1? Because SZ when operates on this minus half, it will give you minus half h cross, but you have taken common plus half h cross, that's why it is minus here. So it was very simple for the SZ case to find out the operator form, but the real problem begins with to find out the Sx and Sy. So why I'm showing you all this, because these are very important when you deal with the relativistic quantum chemistry. There you will be using these Pauli spin matrices. So this is basically called sigma z. So then what are the components of sigma x and sigma y, how to find out those? So that is not trivial, so that's why I am showing you all this derivation, like how to find out these Sx and Sy in this eigenbasis. So one thing is very clear is that, so you have written a square as 3 by 4 h cross 1 0 0 1, and Sz as h cross by 2 1 0 0 minus 1, right? So we have found out the matrix. Now how does this alpha and beta looks like? I think you all know that this is represented as a column vector as 1 0 and beta as 0 1, right? So let's see. So if you operate this alpha This can be derived generally, but as you all know, this alpha is actually a 2 by 1 column vector, that is 1 0 and 0 1. But does it fulfill all the rules? So just for one example, if we operate this s z on this beta omega, so we can write it h cross by 2 1 0 0 minus 1, and you write this column vector and do the matrix multiplication. So this is 1 0 is 0 and 0 1 is 0. Then you are left with so you have h cross by 2 0 minus 1. You can take out this minus here. So now you have the same wave function back, but with the eigenvalue minus h cross by 2. So that's what we have expected, right, for when sz operate on beta. And one more thing is that this alpha and beta, they are obviously they are orthonormal. For example, if alpha dagger alpha, if you see, it's basically so when you write the dagger, so you write it in row vector, and for the real so for the alpha part you write it in the column vector. So and you can see that this is 1 1 and 0 0, which gives you 1. And similarly, for if you do alpha beta, as they are real, so I'm not writing the complex part. So you can see that 1 0 and you have 0 1. So this is 1 0 and 0 1, it gives you 0. So alpha beta, they are orthogonal to each other, they are normalized, and they are the eigenfunction of s square and sz operator. Now let's do the hard math, that is to find out the sx and sy in the matrix representation of sx and sy in this SMS basis, right? So before that, let me tell you the rules that we already know. So s square commutes with sx, and that is s square sy and s square sz. They are all 0, right? And another thing is that sx sy, so I am just deriving, I am not going to derive all this because you all already know this rule from the your angular quantum number, angular quantum operator. So angular operator, so from there you can see these rules are very generalized, because this spin are the this spin can be treated similarly as the angular momentum vector. Then this is IH cross SZ, and SY SZ is IH cross SX, and SZ SX is IH cross SY. Okay. Now, what is our goal? So you can see this s square and sj, they commute, so they have the same eigenfunctions. However, this sz and sx or sz and sy, they do not commute, so they are not going to be diagonal in that basis. So how do we find out the operator form? So in this regard, I will define the operator call S plus, such as Sx plus Isy, and S minus as Sx minus Isy. Now I will write this S plus and S minus in this SMS basis, their operator form, and from there I am going to derive the operator, the matrix form of Sx and Sy. Okay, so that is the actual goal. So from this you can write that if you take sum of this first and second equation, you have S plus S minus 2Sx, okay, and they will cancel out, so you have Sx is equal to half of S plus and S minus. So if you know the operator form of S plus and S minus, you can get the operator form of Sx, right? Similarly, so this we got as 1 plus 2. Now if you do 1 minus 2, then you have S plus minus S minus, and you have 2I Sy. So now you have Sy is equal to 1 by 2y S plus S minus, right? Now there are some certain things that will be needed later. So A square and S plus minus is equal to, so you have S square, and for S plus minus you can write Sx plus Isy, right? And this you can write it as S square Sx plus minus I S square Sy, and from here you can see that S square Sx and S square Sy commutator is 0, right? So it will be 0, it will goes to 0. So actually S square and S plus minus, they commute, so that is equal to 0. Another thing is S plus S minus, what is this? So you can write Sx Isy, Sx minus Isy. So this will give you Sx, and so that will be 0, and you can also take plus I Sy Sx and minus I plus I Syx and minus I Sx, and the final term plus minus, and I square is minus 1, so that is plus, and you have Sy. So this is 0, this is 0, and you can write it as this fellow, you can write it as I Sx Sy, and take a negative here, this is I sx sy. So you are left with minus 2y sx xy, and this is minus, this is I h cross s z. So what you are left with is 2h cross s z. Okay, so the final result is s plus s minus is 2h cross sz. And there are two more things that will be required in the derivation, that is your sz and s plus minus. Okay, so you can write this sj plus s x plus minus I sy. Give me a second. So now you can write this as sz sx plus minus I sz sy, and this sz can be written as, this sz sx is basically I h cross sy, and you have plus minus I, and this is, so you can write it as maybe minus I h cross sx. So you can write it as I h cross sy, and with this minus, this is actually plus minus h cross sx. You can take common h cross, and you have I sy plus minus sx. Which is basically h cross s plus minus, or plus minus this. So the final result, this will be used in the later case. So sz is s plus minus is plus minus h cross s plus minus. And one another thing that will be required, just I need some blank slides. Yes, another important thing that will be required is what is s plus minus, s plus and s minus, and s minus and s plus. So we'll derive this s plus and s minus, then from there we can infer that what will be s minus and s plus. So what is s plus and s minus? Sx I sy times sx minus isy. So that is sx square. Then you have this sy is sy square, and plus minus is minus, and I square is minus 1. So you are left with sy square, and here you have I sy Sx and minus I Sx Sy. So the order actually matters here because the Sy and Sx doesn't commute. So you have to write it in the proper form. You cannot just simply write Sy Sx is equal to Ssxy. So because they do not commute and they are operator. So you have Sx square, Sy square, and then take minus I common. So you will have Sx Sy minus Sy Sx, and this is, so this is x square plus Sy square you can write. So you know that a square is Sx square plus Sy square plus Sz square. So this Sx square and Sy square can be written as S square minus Sz square, Sx square, Sy square. So here I am writing S square minus Sz square. So it is always better to write anything in the form of S square and Sz square, because the eigenbasis that we are dealing with, that S comma ms, so they are actually the eigenfunction of this S square and Sz square. So it is always a better idea to write all the things in terms of S square and Sz square if it's possible. So now you have Sx Sy, and you can write these S square minus Sz square minus I times I H cross Sz. So now you have S square minus S Z square, and this is your plus H cross Sz. So what we have S plus S minus is S square minus Sz square plus H cross Sz, and similarly you can work out that S minus S plus is S square minus Sz square, and instead of this plus sign it will come out to be H cross Sj. Okay, so we are done with the things. So let me just mark it whatever the things that will be needed here. So we need this thing, and we need this and this also in the later course of this derivation. So now our goal is that to write the S plus, as I already mentioned, in the basis of your S and ms, that is in this basis. And to know this, we have to know that how this S plus will operate on this S and ms. So this is our goal. So what will be the outcome? So let's say, so the first thing is that this S plus doesn't commute with Sz, right? So that I think we have shown here that what did I mention? Yes, S plus and Sz, yes, here. So this Sz and S plus minus, they do not commute. So obviously this S plus is not, so that this alpha and this beta spin, they are not going to be the eigenvectors of S plus and S minus, right? So instead what we can do, let's find out this quantity Sz operating on S plus and SMS. Okay, so here we can use this relation, that is this Sz and S plus minus commutator. So we have, let me write down for, so you have Sz S plus minus commutator is equal to plus minus H cross S plus minus. So you can write this equation as so this you can write it as Sz S plus minus S plus minus Sz equal to plus minus H cross S plus minus, right? And this you can write it Sz S plus minus is equal to plus minus H cross S plus minus, and this will be this will go here, so you will have plus S plus minus Sz. Okay, so let's generalize these things. So how this S plus minus will act on this SMS? So in a single go we'll get the equation. So this you can write it from here. You can write it H S plus minus plus S plus minus Sz. So this as a whole operating on this wave function S plus minus sorry, not this, only this. So it's operating on SMS, right? So this you can write as S plus minus SMS, and now you can see this Sz can operate here, and you all know what will be the result. It will be MS H cross times the same function SMS, right? So you can now take common this H cross and S plus minus from here. So you can now take common let's say, so if I take common this H cross from here, so what I'll be left with? So I'll have MS plus minus 1. So let's write it in this way, plus minus 1, and from here the only MS will be left. So now you are taking common this H cross from here, right? And now you have S plus minus operating on SMS, right? Carefully look at this. So, or we can rewrite this as MS plus minus 1 H cross S plus minus SMS, right? So what did we get actually finally from this expression? So just let me write it for clarity here. So when Sz is operating on S plus minus on this SMS here, so what we are actually getting? Please carefully look at this equation. So now you can see that it's like this whole this S plus minus operating on this SMS So this will also return a function, right? Because this operator is operating on a function which will return you a function. So that's how operator works. So now, so this function, this whole function is an eigenfunction of this SZ operator. And what is the eigenvalue? That is ms plus minus 1. So ms plus minus 1 h cross, and you are getting back the same wave function, right? So what we can infer from here is that it's like when s plus minus operating on this sms, so how can we get this ms plus minus 1 h cross when s jet operate? So this can only happen if sz is operating on s ms plus minus 1, right? So it's like it is now you are getting ms plus minus 1 h cross and the same expression, right? So it's like now we can write, so from here if you see this expression and this expression, now it must be clear that when s plus minus operates on sms, it's proportional to s ms plus minus 1. So it's like when s plus minus operate on this sms, it is not affecting the first quantum number s, but actually the second quantum number is getting up by plus 1 or minus 1. That's why this s plus minus are called ladder operator. Okay, so let me again explain this once for your clarity. So we have got this. So we didn't know that how this s plus minus works on this sms, right? Because they are not the eigenfunction of sms, right? But instead we tried to found out that how this sz s plus minus sms will come out to be. And what did we get is that when sz operates on this function, we get back this same eigenfunction with an eigenvalue, that is ms plus minus 1 and h cross. This eigenvalue can only be achieved when this sz operates on this s and ms plus minus 1. Right, so what's happening is that this s plus minus or this operator is actually taking the initial state, that is sms, to a plus 1 up or minus 1 down from the its original state. So that's what we are getting. So it's proportional. So we don't know the proportionality constant, so we can write it as c plus minus, right? So now our goal is that how to find out this proportional constant. Now if we can find out this proportional constant, then our job is done. Okay, so let's try to find out this c plus minus 1. So how are we going to proceed in this way? So you know this sms, they are the eigenfunctions of s square and sz operator. So they are definitely normalized and orthogonal, right? So we can write sms dagger or so they are giving you this function, right? So you can write actually s plus, yes, so you can write this s plus minus, or I should just write, let's just try to find out the only one constant, then I can generalize the. So I am, in this case I am finding out this c plus constant. So if this operates on s plus, and you are taking the conjugate of this, and then you have s plus sms. Okay, So now what will you get? So this will give you C plus star and dagger also when this operates on this. So let me write it in this way. Now you have ms plus 1 dagger, and here you have C plus S ms plus 1. Okay, now I think you know this. AB whole dagger is B dagger A dagger, right? So how will you write? So this C plus is just a constant. So please, this is not a dagger, this is a plus for this sign. So you will get a conjugate of this, and this kate will be a bra function. So this is ms plus 1, and here you have s ms plus 1, and I'm writing this C plus here, and these are normalized, right? Because they are the eigenfunctions of again s square and sz. So this will be 1, so you are left with C plus whole square. Okay, now we can write this. So let me again write this expression here: s plus s ms dagger and s plus sms. So as I've just mentioned that AB dagger is B dagger A dagger, so this you can write it as sms s plus dagger. So s plus is sx sy. So what is the dagger of s plus? Sx minus sy, which is s minus. So this is basically s minus, and now you have s plus here and sms. Okay, so now we'll use this property of s minus and s plus that I have derived. Let me just show you. This s square minus sz square minus h cross sj, this property. Now you can put sms s square minus sz square h cross sz sms. So now this whole thing is diagonal in this basis, right? So what you will get actually, because this s square when operates on this sms, you will get s into s plus 1 h cut square, and when this sz square operates on this, you will get ms square h cut square, and when this operates on sz, so you are left with ms h cut square, and this sms and sms, they are actually 1 normalized. And so here we got C plus mod square, and the same function is giving you this value. So this is C plus mod square is equal to this, right? So we can again take h cut square common, and s plus 1, and here you can take ms common. So now you have ms plus 1, right? So your C plus becomes h cut root over of ss plus 1 ms ms plus 1, right? And similarly you do this, you will get c minus s h cross s into s plus 1. Now our job is done. So now we have just to find out the s plus operator, how will it look like in that basis. Then from the s plus operator, as I've mentioned in the previous slides, that from that s plus operator you can get the sx and sz operator, and from that sx and sz operator you will get the other two Pauli matrices. So that is just very straightforward, but I'll show you. So now here you will get ms minus 1. Okay, so in the electron spin case, this s is half, so this is basically, you can write it as h cross, then 3/4, because s is half, so I'm just putting the value s equal to half. So now you have ms plus 1 h cross 3/4 minus ms minus 1. Okay, so having known all of this, now our job is to find out how the s plus operator will look like in this basis. So for just for clarity, we have to find out this matrix elements, right? Half s plus minus half, then you have minus half s plus half, and you have minus half s plus minus half. So what do I mean by this plus or minus half? As I've just mentioned again before, that this your half plus half I have denoted as half, and half minus half as minus half, just for clarity of notation. Okay, so we know when s plus operates on SMS, you will get c plus and s ms plus 1, right? And we have already found out that what c plus is 3/4 minus ms plus 1. So now when this s plus operates on this half, so it will be 0, right? Because there is no so this is a two-level system. This is minus half and plus half, and it can be shown that when operates on the top level, this s plus, there is no place left to make it go higher, right? So it will be 0. So eventually this matrix element you will get 0. Now what about this? When this s plus operates on this minus half, it will actually take you to the plus half level. Okay, so now this matrix element will survive, right? So this will survive, and we'll find out like what will be the element. Now look at this. When this s plus operates on this half, again this will go to 0, and this went to 0. And what about this case, right? So when
Sir,
this, yes.
sorry, I actually joined late. I am not understanding like how you got this matrix.
Okay, so you want me to know like how did I get these matrix elements?
Yeah,
Okay,
yeah.
so actually any operator, so uh, let's say any operator A. Okay, so any operator you can write it as a unit operator times A and one unit operator, right? And this unit operator, so I think you all know that the projection, the resolution of identity. So in the basis you are working with, so you can write this as summation of phi m and there is this a operator, and again this unit operator you are expanding, this is in another basis, let's say like the same basis but with different dummy index, that is phi n and phi n. So this is mn. So now you have mn, and now this is the matrix element, right? And that is your mn, and you have phi m, phi n. So in the basis that you are working with, this phi I or phi m or phi n, so you can write that any operator in that basis. So here our basis is actually half and plus half. This is one basis, and you have another basis, that is half minus half. This is your alpha spin and this is your beta spin. So I am representing my s plus or s square or sz operator. If you just for your clarity, I have shown, yes, this s square operator. So I have written this s square operator in this basis, this half and half and the other matrix element. So here I have found out this, its matrix form. How does it look like? Then sz. Now it was not trivial to derive the operator form of sx and sy. So how to derive that? That was my goal, and from here you can see that this sx operator you can write it in this ladder operators form, s plus and s minus. So if I know the operator like the matrix form of this s plus and s minus, I can get back the sx. So now is it your like your question is answered?
Yeah, and like why you are choosing plus like half plus half and half minus half as the basis? Like,
So yes, so this electron spin is just same like your orbital angular momentum. Okay, so and it was found out that the spin quantum number of electron is half. Okay, so it has only two possibilities because your ms will only vary from minus half to plus half. So this thing I have already told in my very first slide. So you have only two possible, ms and minus half and plus half. So you have only two options,
okay,
that is half plus half and half minus half. And that thing it actually represented by 1 0 and 0 1. If you see, if you will see the recordings, then it will be, I think, clear for you.
okay, sir.
Okay, thank you. So okay, so just let me erase this part, and we are almost done to get this matrix elements. I'm sorry. Okay, so this will be 0. So and this will have some value, right? Now how about this case? Now if this operates on this minus half, it will take you the plus half, but here you have minus half. So because of the orthonormality condition, again this will goes to 0, right? So let's find out what will be the when s plus operates on this minus half, what will be the c plus, right? So and we have seen that this c plus is s plus 1, or that is 3 by 4. So you will get h cross 3 by 4, and your ms is minus half, so it will be plus half, and you have minus half plus 1, right? So this is your half, so h cross 3 by 4, and 1 by 4, and this is basically H cross. Okay, so how our matrix elements will look like? It will be 0, it will be H cross, and this is 0 and this is 0, and you can take out this H cross common, so it will be 0 1 0 0. Now we'll do the same exercise for S minus, and then we'll get our matrix, desired matrix element. So what will be for S minus? So again, let's write out the matrix elements. It will be half S minus. So in the next class, I'll show you a very detailed derivation of how you can write the operator in the matrix form and how you can diagonalize it. How can you do the unitary transformation to get the diagonal elements and all those stuff I'll discuss in the next class. So as of now, let's write out the matrix elements. So you will get half S minus minus half, and you have minus half S minus and half, and you have minus half S minus and minus half, right? So this S minus, when will operate on this half, it will take you to minus half step, and because this half and minus half are orthonormality, orthonormal, so you will get 0 out of here. And when this S minus operates on this minus half, so there is no further down level, so this will also be 0. And when this S minus, so this is also 0. And how about this case? So you can see this minus half will take you to this minus half level, and because of this bra minus half, this matrix element will survive. And you can work it out from these equations, how the C minus will look like, and you will see your S minus will have the form H cross 0 0 1 0. So this is your S minus, and we got S plus as H cross 0 1 0 0. Let me see, right? Yes, 0 1 0 0 0 1 0 0. Now we have shown your Sx, you can write it as Sx is equal to half of S plus S minus, right? So you see this light. What did I write? Yes, from this expression, Sx you can write as half S plus S minus, and Sy you can write it as 1 by 2 I S plus S minus. Is this plus? No, sorry for the mistake. It will be minus, because see here I have taken the minus, but I have written it as minus here. It was minus, but yes, it will be, sorry, this is wrong. So your Sy is just a second. Yes, 2 by S plus S minus. Yes. So there was a slight mistake. So you can now write the Sy as 1 by 2i S plus S minus, or you can just multiply I here and I here, so you will get minus I by 2 S plus S minus. Okay, now you just do the matrix summation. So S plus and S minus, so you will get H cross and 0 1 1 0, and here you have Yes, so there is one half here. So now here you have minus I. Yes. So here you have minus I and minus I h cross by 2. Now s plus and s minus, so you will have 0 minus 1. No, s plus is here, so it will be s plus, it will be 0, it will be 1, and it will be s minus, so it will be minus 1 and it will be 0. Now you can take out take in this minus I here, so now you will be left with h cross by 2, 0 minus I, and this is plus I and 0. Okay, so finally you can write Sx as h cross by 2, 0 1 1 0 sy. In that basis, what was actually our goal? H cross by 2, 0 minus I 0, and sz, that was diagonal 1 0 0 1. Okay, so these are actually your Pauli matrices. This is sigma x, this is sigma y, this is sigma z. So this is a non-relativistic course. However, when you go to this relativistic region of the quantum chemistry, and there you will see this sigma s, sigma y, sigma z plays a very important role. And now you can write this Sx as h cross 2 sigma x, sy as h cross by 2 sigma y, sz by 2 sigma z. Okay, so we have written down the in that basis how the sy and sz will look like. Okay, so one very important property of these Pauli matrices is that, so do this on your own. So if you see this sigma square or sigma y square or sigma z square, let's do it for sigma x square. So what do I mean by that? 0 1 1 0 times 0 1 1 0. So if you see, this is 0 0 and 1 1, so it is 1, then you have 0 1 0 0 0, and here you have 1 0 0 is 0, and that is 1, and which is a identity matrix. So sigma square, sigma y square, and sigma z square, this is 1. And if you look at the trace, and what do we so what is the meaning of a trace of a matrix? So trace of a matrix is basically the sum of its diagonal elements. So if you take the any trace of sigma x or trace of sigma y or trace of sigma z, you will see this is 0. So 0 0 0 0 and 1 minus 1, they are all 0. And there are many other interesting properties of this. So to mention few, this is 2. And so now a very important concept is that, let's say you have a spin function. I don't know the form, but it's a function of spin, right? Now if I operate my sz operator on this function, I have two probability, right? One is that I can get that minus half step, a plus half step, or minus half step if I operate this signal, because this function I can anyway write it in the as a linear combination of this 2 spin function. Okay, now let's say I operate on this minus half this eigenfunction SZ operator. What will I get? So here we'll also get a minus half, because now my state is frozen in this minus half state. So initially this f omega, I didn't know what was its form, but when I did perform this operation on, or I measure the sz on this function, I am getting either of these state, like I don't know. So but this is called the wave function collapse. But another interesting thing is that now on this function, if I operate Sx, what will I get? Any answer?
Can you once repeat like what happens when operating sz on minus half?
So so now your state is defined, right? Because this minus half is an eigenfunction of your Sz operator. Now if you do measurement any times, like if you operate S square and Sz on this function, this is the eigenfunction of the Sz operator. So you're from your basic quantum chemistry postulate, you know, if that a state of a system is the eigenfunction of that operator, so then like many times you do the experiment, you will get back the same eigenvalue. So that's what happening here. So if you operate, so now your system, like system state is frozen in minus half state, because if you have performed one time operation. So now you are, like, it doesn't matter how many times you are doing this SZ operator in this minus half state, you will actually get back this minus half state. So now my question is that on this minus half state, if I want to measure the Sx, so what will I get? So the answer to this question is that now this minus half state is no longer a eigenfunction of this Sx state. It was of Sz operator, but it is not an eigenfunction of Sx operator. So again, you have two probability, because you don't know the eigenfunction of Sx, but anyway you can form another eigenfunction, so which is a eigenfunction of Sx. So you will have two probability, either this half x state or minus half x state. So what do I mean by this subscript x? Now these are the eigenfunction of Sx operator, not Sz operator. So again, if you operate Sx on this, you will get back this same state. But if you operate this Sz, now you will get again half and minus half, because this half x was not the eigenfunction of Sz operator. So this is a very thought experiment. So just to show you the what does I mean by operating on a linear wave function, so linear combination of wave function, and how does these eigenfunctions and eigen operations matter. Okay, so the final goal was this, to get the eigen matrix elements of these Sx, S1 and Sz. Now what we'll do is that let's solve this problem, then we'll do the summary and we'll practice some question. So the question says, find the energy levels of a spin S is equal to 3/2 particle whose Hamiltonian is given by this. Alpha and beta are constant. Are these level degenerate? So can you try once to, so whether these levels will be degenerate or not? It's a very simple question. give me 2 minutes. So by the time you solve this question, have you solved the question?
I'm not able to do it.
Okay, actually this is very simple. Let me show you. So your Hamiltonian was given by alpha h cross square sx square plus sy square minus 2sz square minus beta by h cross sz. Right. Now you know your eigenfunction is basically SMS. Okay, but you know this is x and sy, it cannot operate like it's not the eigenfunction of sx and sy. So we can write it as, so this alpha and beta are constant, so we can write it this as s square minus sz square minus 2sz square minus beta by h cross sz. Now this is basically your alpha h cross square s square minus 3sz square minus beta by h cross square sz. Right. Now so your spin is, in this case, is 3 by 2. So what are the values of ms possible? Plus s2 minus s. So 3 by 2, 1 by 2, minus half, and minus 3 by 2. This is the 4 possible ways, right? So the question asks whether these states, that 3 by 2, 3 by 2, 3 by 2, 1 by 2, 3 by 2 minus half, and 3 by 2 minus 3 by 2 are degenerate or not. Now if this operates on, so if this operates on this SMS, what you will get? You will get actually alpha. So now I am writing the energy. So now you will get alpha by h cut square, and now you will have s times s plus 1 h cross square minus 3 ms square h cut square minus beta by h cross. Actually I didn't need to solve all this. but ms h cross. So your energy expression actually depends on these ms values. Okay, if your energy expression was independent of ms, then you could have said, okay, all the levels will be degenerate. But as your energy levels depend on this ms value, so the answer will be these levels are non-degenerate. Okay.
Yes, yes.
Okay, so now then we will solve this question. So let me do the summary what have been done in this second week. So the thing is that we don't know the exact solution of a many body particle, say 2 electron, 3 electron and n electron system. So we have to uh, hold some kind of approximation method, and two promising approaches is that one of this variational theory and another is a perturbational theory. Okay, so in the context of variational theory, it was discussed first the Euler's variation, which said that uh, if you vary over the entire space of your Hilbert space, then the stationary of the expectation value, that is actually psi bar h psi bar, if you vary over the all space, then the stationarity of this expectation value is basically the eigenfunction of the Hamiltonian. But again, this imposes one very big restriction is that you have to vary over all space, and which is not possible, and that's why it is not of no use. Now the Rayleigh-Ridge variation. In the Rayleigh-Ridge variation, it was said that if you take any trial wave function psi bar h and psi bar, and this quantity is greater than or equal to E0. Okay, so that was the Rayleigh-Ridge principle. So which says that this quantity will be, so there is always a upper bound to this trial wave function. So E0, so you can get at max E0 if this psi tilde is your exact wave function as a ground state, but other than you will have always energy greater than the ground state energy. Then it was discussed the linear variation principle, so where you have expanded this psi bar as a linear combination of some eigenbasis phi I, and there it was very thoroughly discussed that here you can have that your in case of linear variation, so if this is the order of the exact energy, then in case of linear variation, so whatever the stationarities you will get, so let's call this as E0, E1, E2, E3 and some. So in that case, they will be at the upper bound of this state. And there it was beautifully proven that for any two solution there is only one exact solution, and that was a separation theorem that was being discussed. So that was a variational principle. Now the to get that one single most important determinant, that was this psi bar h psi bar, provided that your psi bar is normalized, and you have then formed the Lagrangian on based on this chi I, chi j, they are actually delta ij. So now you have to vary this variationally optimize this psi bar, and for that you actually need the Slater rule. So there Slater rules was discussed for this kind of system, psi h psi, just the expectation value. So there this h was actually summation of your one particle operator and this 1 by Rij term, and when this Hi operates on this this Hi is put in between this psi and psi, you get actually a very simple like equation, which is summation of chi I h chi I, and like that. And for this Rij case, it was shown that this is anti-symmetrized integral, right? So these were discussed, and then one important property of this anti-symmetrized integrals. So these are very crucial in your electronic structure theory that people do in the quantum chemistry domain. So this very important property is that if you this is called anti-symmetrized integral because if you just switch one of them, so this is basically the negative of this. So for any integral of ABCD or IJKL type, if you just switch two indexes, actually this is a negative of the previous one. So that was mentioned. Then you will, in the later course, you'll also see that if this psi and this psi differs by only one spin orbital, then how the rules will come out to be, and if they also differs by two electron, then two spin orbital, then how the rules will come in. That is your Slater rule number 2 and Slater rule number 3, that will be discussed in the coming weeks. So then so after getting this
So currently we have only
yes.
so currently we have only learned like the first Slater's rule, which is just the expectation value is the summation of the Hamiltonian plus the Coulombic term.
Yes,
Uh,
yes.
is it
So
that?
yes, so that's what you have learned so far. So in this week, in the week 2, you have learned only the what will the Slater rules in the expectation value approach. In the later course, when I think the CIS will be discussed, like configuration integration interactions singles, and the molar placid perturbation theory 2, which is a very big milestone for this course, and there I think it will be discussed for the Slater rule type 3,
Okay.
and so these are only 3 rules that you have to remember. And then what was performed is that the spin integration was performed. So getting the spin orbital expression, the spin integration was performed based on that in any spatial for the closed shell system. Then it was generalized to the open shell system also. So what is closed shell? So that definition was also given. In the case of closed shell, there is the spatial part of a half number of alpha spin and half number of beta spin are same, and the electron numbers are even, and all those stuffs were discussed. And then a very important thing was discussed, that the exchange interaction. And so this is not quite physical. You cannot actually explain the exchange integration. So just let me quickly tell. So you can write this xi xj as xi xj 1 by r12 xi xj minus xi xj 1 by r12 xj xi. So what is that? That the electron 1, electron 2 in the Dirac notation 1, 2. So again 1, 2, 1, 2. So this term is Coulomb term because the electron 1 is sitting in the same orbital here, xi and xi, and another electron is sitting at xj. So it's kind of a Coulomb interaction between two electrons that is sitting in one in xi and one in xj. So that's why this is very physical, and that is there in our regular physics, classical physics, that this is a Coulomb interaction term. However, this exchange term cannot be described classically. This is purely a quantum phenomenon, and you cannot, there is no classical analog to this. So it's like your electron 1 in sitting in xi and another electron in xj, and the same time you can see that the electron 1 is at xj and xi. So it's totally a quantum phenomenon, and that is purely coming because of the indistinguishability of your electron. So that's why this term come. And as I mentioned, that this integral, that is this exchange integral, that is positive, and because of this it is coming as a negative term. It has a stabilizing effect. So that was discussed, and that exchange interaction only occurs between two parallel electron spin. And then finally the week was concluded by showing you the Lagrange variation. So the problem was defined for the Hartree-Fock, that if you do a Lagrange variation for the Lagrangian with respect to the both the your orbital space, so you will optimize the orbitals to get the best determinant possible, and the Lagrangian what I should say, the Lagrangian constant. So then you will get the Hartree-Fock orbitals and Hartree-Fock determinant and energy and all that. So that was discussed. Now let's try to,
One doubt, like
yes.
uh, so the Rayleigh-Ritz variation says that there is always a like we can't get energy lower than E naught. So what's the difference between Rayleigh-Ritz and Euler variation statements? Like,
Okay, so Euler's variation is that if you know, like, if you, so let's say you want to find out the eigen function or eigen state of the interest of your system, right? So it has some eigen value. So because the quantum
mm,
mechanics says that, let's say you have a system and you measure something, you want to measure something on this. So so whatever the value you are getting, it's actually one of the eigenvalue of that operator, but you don't know the eigenfunction. So that's a
mm,
different problem. But
mm,
to find out the that
mm,
eigenfunction, that is, that must be a part of any Hilbert space, right? So if you are operating, like if you are measuring
mm,
something, that means that is Hermitian, and its eigenfunctions will be like orthonormal, and they will follow all the rules of this Hilbert space and all. So so now
mm,
that is there in the Hilbert space, but you don't know. So the Euler's theorem says that if you search over all the functions over the all the over
mm,
this space, then you will get the whatever the stationary condition you will get. So that is actually basically your H psi is equal to E psi. But the problem is that you cannot get hold of all this space. So that was the Euler's theorem. And
mm,
but in the Rayleigh principle, what did it say? That you take any trial function, and it was actually proved, and it was, the proof was very simple. And so in that case, you don't know the exact solution, but your trial function, it was shown that its expectation value is always greater than the your ground state energy. So that's actually different.
So Euler's variation does not talk about E naught, like the minimum energy.
Uh, no, like you can get any energy, E0 excited state, and so whatever the system you are interested in, like E0, E1,
So it
E2,
just says that if we span over the entire Hilbert space, then we can get the minimum energy.
you can get the
Does it say?
actually eigenfunction and eigenvalue as the stationarity of that
Or
psi
like the
H.
best eigenvalue we can get.
What do you mean by best eigenvalue? So
Uh, I mean the minimum energy. Sorry.
yes, so obviously eigenvalue is a spectrum, right? So any Hamiltonian, so whatever the, so actually the what is the definition of ground state? Ground state is that you have a Hamiltonian, like you have a energy operator, and you, let's say you got 10 eigenvalue. whatever is the minimum, that is your ground state. That is actually the basic definition of any ground state, and whatever lies above that state or above that eigenvalue, those are your excited state.
Okay.
So so let's solve this question. So today I'll solve this question, but in the next class I'll show you like why did I solve this expression. So in the second class, when I'll talk about this diagonalization problem of any operator matrix, then I'll connect this question with with whatever I'll derive in that class. So it is given that for any symmetric matrix, what do I mean by symmetric matrix? In case of symmetric matrix, your off diagonal element, that is O12, or this was O21. So these are actually same. This is O12 is O21. So the definition of any symmetric matrix is that A is equal to A transpose, and the diagonal elements are basic, so there no need to say. So now your trial vector is C. So this is your trial vector, which is cos theta sin theta, and calculate this theta for which this omega theta, that is C dagger OC, is minimum. So let's solve this. So we have to find out this C dagger OC. So your omega theta is C dagger OC. So dagger is written as a row vector, and you have O11, O12, O12, O22. Now you have cos theta, sin theta. So now you have cos theta, sin theta. Now here you have O11 cos theta plus O12 sin theta, and here you have O12 cos theta plus O22 sin theta. Now if you do this matrix multiplication, you have O11 cos square theta plus O12 sin theta cos theta, and here you have O12 sin theta cos theta, and that is your O22 sin square theta. Okay, so this is your omega theta. Let's make it simple. So now you have O11 cos square theta plus O22 sin square theta. I'm taking this here, and you can O12 sin theta cos theta, so you can write it as O12 2 sin theta cos theta, or I need a blank slide. So the omega theta is O11 cos square theta O22 sin square theta plus O12 2 sin theta cos theta, that we can write it as O12 sin 2 theta. Okay, now we have to find out the optimal condition, and from that we have to do d omega theta d theta is equal to 0. which will give you so this is your form of omega theta. So now it will give you 2. So if you do this derivative with respect to theta, you will get 2 cos theta minus sin theta. dd theta of cos theta is minus sin theta. Now you have O11, and here you have 2 sin theta, and dd theta of sin theta is cos theta, and you will have O22, and here you will get O12 and O12, and the sin 2 theta is actually cos 2 theta, and there is this 2, because this 2 theta, when you do this dd theta, it will come out to be 2, and that is equal to 0. So now you have minus 2 sin theta cos theta O11 plus, so I can as write this 2 sin theta cos theta as, I can write it as minus sin 2 theta O11, and I can write this as these 2 sin theta cos theta as sin 2 theta O22, and I can write it this as so I can take it this O12 cos 2 theta this side, so it will be 2 O12 cos 2 theta. Okay, so now if you take common sin 2 theta, so you have O22 minus O11, and here you have, so if I want to get rid of this minus sign, what I can do is that I can absorb this minus sign here, so this will be your plus sign, and this will be minus sign, and this minus sign will go away. So actually what you have, so just a step jump, you will have O11 minus O22, and here you have O12 cos 2 theta. Okay, so now divide both left hand side and right hand side by cos 2 theta. So now you will have tan 2 theta O11 O22, and here you have 212. Yes, so now you can take this to this side, so you have tan 2 theta is equal to 212 O11 minus O22. Now you can write 2 theta is tan inverse 212 O11 O22, and your theta is 1 by half tan inverse 212 11 22. So this is your solution. Now I'll come back to this solution, why it was like it is important, like this theta is equal to 1 by half tan inverse and this c. So the answer to this question is that calculate the theta for which your W theta is minimum. So that is the answer, and that we got. So for this value of theta, I'll get the minimum is omega theta, and if I put this theta back in this equation, I'll get the one of the eigenvalue of this O12 operator. That will come in the next class. So this is very simple, just tell the answer. This is already discussed in the class, or still? What will be the answer?
Option 4, I guess.
Yes, the 4 is the answer. I think this is very straightforward, because if you increase the number of bases, like here the number of bases was 2 and here the number of bases is 3, and as I discussed in the linear variation, so if you increase the number of bases, actually your first eigenvalue is less than or equal to than the second one, and also the in the second case also it goes the same way. However, for the 1 2 3 option, you will see that one or either or neither uh, of these two equation will not be valid. So this is very simple, and now I'll not solve this question totally, but I think this is a very good practice problem. So I'll just sketch what you need to do. So first, see that this normalize whatever the trial wave function is given. The very important thing is that uh, it should maintain the boundary condition. So what was the boundary condition for particle in a box is that when x is equal to 0, your psi should be 0, and at x is equal to a, your psi should be 0. So from this trial wave function, so you cannot take any wave function. So you couldn't have any taken, let's say, x square or x cube plus 3x minus 6, those kind of stuff, because that will not follow the boundary condition, and that is not an acceptable wave function for that particular type of problem, that is particular one dimensional box where the wave function must have to be vanished near the wall. So so uh, so the psi is given, and it is stated that the function is normalized. So what you have only need to do is that you have to calculate this psi h psi and psi bar. Now this is 1, right? So you have to only calculate this expectation value. So your Hamiltonian will be, for this case, minus h square 2m d square dx square, not del square del x square, because here you have only 1 degrees of freedom, so you can use this d square dx square. Now you have to take this integral and then calculate the energy, whatever the energy you'll get, and the true ground state energy is given. So let's say this E, you will get something, let's say this is E dash 0. Okay, and now you will get, because you are integrating it out, right, all the variables, mean there is only one variable x, so you will obviously get one number, um, uh, which will be in order of this value, h square by 8m square, you can definitely get. Then you can write this E0 dash minus E0 divided by E0 into 100% to get that percentage of error in the ground state energy of the particle. Okay, so this is a very simple question, and this is the reference that I have taken, and okay, so we'll conclude this session here. Anyone has any doubt? Deeptanu, do you have any doubt regarding this week?
Uh,
So one doubt, like that
Hmm.
in the Coulombic and exchange terms, like if
Hmm.
we interchange the indices, like J1 to, if we make it J21, both are equal, right?
Uh, Sorry, I couldn't follow.
Like J12 is equal to J21, right?
So you are talking
The
about the
Coulombic
exchange
term.
integral.
Coulombic and exchange both, like.
So you are just focusing only one of these term, right?
Yeah, yeah.
So you
One of
want to
this.
switch between 1 and 2.
Yeah.
So let's write it explicitly. Maybe I'm not getting your question. So you want me to
So this term is J12, I guess. So if we just write J21, so
J21. So you want me to write in this fashion?
uh, I think
And
INJ should remain the same.
yes, actually you can change. So maybe if I'm getting your question correctly, so this is equal to actually xi
Two.
uh,
Yeah.
2xj1 1 by r12 and xi2 xj1.
Yeah.
Yes,
I
so
had a
but
doubt in that
actually,
only.
we write this. So this is the way I have explicitly mentioned the coordinate, but actually in Dirac notation we write one electron in spin orbital and second electron. So actually this is your
Oh, okay.
xji. I'm not
Okay.
writing
Okay.
and this is
Okay.
xi xj. So it's like
Okay.
flipping these two orbitals, right? So you can actually, there is eightfold symmetry. I think that is being discussed already. Now it's clear.
Yes, sir.
Okay. Okay.
Thank you, sir.